Let's see what's next. Actually, there's a 4. Let's look at it too. And then we'll look for stuff that actually has potential energy in it. Or not potential energy, but electric potential. So we've got those charges at an equilateral triangle with sides of that. What's the potential energy of the system? So this is just like that square one that I kind of sketched real quick. So you've got 3 charges that are all 1.4 times 10 to the minus 6. And they're on a triangle. And the sides are 0.25 meters long. Right? So the potential energy for making one pair is just 9 times 10 to the 9th, 1.4 times 10 to the minus 6, and they're both 1.4, so both the charges are the same, so that's why it's squared. And then divided by the distance, which is 0.25. So that's the potential energy for making one pair of charges. And if I look at all the pairs are the same. So just do that and times 3. Let's punch that in real quick. 27 times 1.4 squared divided by 0.25. So 211, and it'll be 10 to the minus 3rd. So that'd be 0.212. Did my arithmetic right. Cool. All right, let's find some actual electric potential stuff. That's the big thing for this. It's easy, but we'll see if 11 has electric potential in it. Yes, okay. You've got 2 large metal plates, carry opposite charges equal magnitude. They're separated by 45 millimeters. The potential difference between them is 360 volts. So what's the magnitude of the electric field assumed to be uniform in the region between the plates? That was kind of the one example we already did. We said if you've got parallel plates, E is constant. And, well, we did for if you're somewhere out in the middle, but if you go all the way across, the potential difference for the plates is just going to be E times D, right? We basically already wrote that down. So, going back, 360, that's 0.45. So 360 is E times 0.045. Not too difficult. You like that algebra, don't you? So apparently we got 8,000 for E. Oh, I should say one more thing. The units for potential. So the unit is volts. So I'm sure you've heard the word volts sometime in your past, haven't you? All right. What's the magnitude of the force this field exerts on a particle with charge? That right there. So again, we know electric field is just force per unit of charge, right? So if I know the electric field, all I need to do is just multiply that by the charge. Right? So I've got my electric field. then times, oops, okay, 8,000 times 2.2. And nano is 10 to the minus ninth. So if I move that, this is 10 to the fifth, so 1.76 times 10 to the minus fourth. Again, if I did my arithmetic right. View somewhere else. Oh. Magnitude of force on a particle. So, did I get my decimal in the wrong place? So 8,000 times 2.2. That's right. That's, oh, that's, no, sorry, that's 10 to the fourth. So this would be 10 to the minus fifth. Apparently I can't do arithmetic right. But yeah. All right. Let's jump down to about number 20. See how it is. So you want to accelerate a proton from a velocity of that to a velocity of that. Through what potential difference must the electron pass? So again, it's just like last semester. If you want to change velocity, that means you're changing kinetic energy. If you're doing that, I mean, you're going to change potential energy. So it's just changing potential is going to be the same as changing kinetic. So I've got 1.5 to 8.5. So I'm doing an electron. I want to go from 1.5 times 10 to the sixth meters per second to 8.5 times 10 to the sixth meters per second, right? So we learned last semester, initial potential minus final potential is the same as final kinetic minus initial kinetic, right? And the only thing that we're doing different now is, hey, now we know that this potential is the same thing as the charge times the potential difference. Right? So all we're going to do is we're going to find the change in kinetic and then divide it by the charge. We got it, right? So we know the charge of an electron. I don't remember the mass of an electron offhand. So let's ask almighty Google. Yeah, I think it's 9.1 times 10 to the minus 31. Electron, the mass is, okay, that's great. That's 1/836 of the proton. I was looking for a number though. Let's try that. Okay, right there. 9.11 times 10 to the minus 31. Okay. Remind me, what's kinetic energy formula for it? This is back from last semester. Okay. This is the one you need to know your dying day, at least if you keep doing physics until your dying day. But yeah, so kinetic energy is 1/2 mv squared. So we're going to go 1/2 9.11 times 10 to the minus 31. And that's going to be the same in both of them. What's changing is the V. So I've got 8.5 times 10 to the sixth squared, and then minus the initial, so minus 1.5 times 10 to the sixth squared. Okay. Let's run the calculator. 8.5 squared minus 1.5 squared is 70, and that's times 10 to the 12th. Well, we're going to do the other part. So times 9.11 divided by 2 is 318. Okay. And what's the exponent on it? Well, these are squared, so those are both 10 to the 12ths. And then 10 to the minus 31 makes 10 to the minus 19. So 3.19 times 10 to the minus 19. So that's the final kinetic minus the initial kinetic. And again, the last thing is, well, that's equal to Q times the potential difference. So just divide that by the charge and we're done. So the potential difference is just that divided by Q, which is negative 1.6 times 10 to the minus 19. So 10 to the minus 19s happily cancel. So divided by 1.6. I got 1.99. Let's try it. It's probably going to say check your signs. It did not say check your signs. It means our arithmetic was wrong somewhere. I really need to get a better calculator for this class. I feel like I type things in wrong a lot. I got one of them off, so I just need to bring it down here. Okay, so let me start over one more time. So 9.11. Oh, actually. Okay. 8.5 squared minus 1.5 squared times 9 point divided by 2 is that. And then for the exponent is 10 to the 12th. And, yeah. Okay. In interest of being speedy. Oh, okay. So we did the right thing. For some reason, I just came off from the decimal. So I'm not sure what. Oh, that was me being stupid. I wrote that down wrong. Because the calculator said it was 319. And then I was like, okay, yeah. So just erase those 3 decimal points and we're fine now. Wow, okay. Okay, so for the same thing, if it's going to be slowed down from that to a halt, you're going to do exactly what we just did. The only difference is now the final is 0, so you change that one to 0 and change that one to 8.5. But otherwise, it's exactly the same. So let's go ahead and do it just real fast. It shouldn't take very long. So 8.5 squared. And then, oh. All right. 8.5 squared times 9.11 divided by 2 divided by 1.6 is 205. So nothing's always in the way, no matter where it is on the screen. Okay. So real quick before we leave this, notice when we went to, so on the first one, we started at a lower potential and went to a higher potential because when we subtract them, we got a negative, right? So when you go to a higher potential, notice the electron speeds up. And same thing on the second one. I mean, it slowed down, and sure enough, our initial potential was higher than our final potential. So it's kind of backwards what you would think, because usually you think, hey, if you get to a higher potential energy, that means you have less kinetic, you should slow down. And that's exactly what's happening. But the thing is, the potential is not potential energy, it's potential energy over charge. And the charge is negative. So that's kind of the unfortunate thing. Somebody got it wrong when they decided to call electron a negative charge, because now it makes everything feel backwards. So normally you would think, oh, higher potential means less energy, but actually no. Yeah. So that's all you need to just remember, is that, hey, when an electron moves to a higher potential, it actually speeds up, and that's because it's an electron. The charge is negative.